Good afternoon, dear students. Today we will be taking up the stereochemical aspects of some name reactions, a net gate perspective. So, assuming we have a background of stereochemistry, let us see to some important name reactions. But prior to that, let's just review the contents and go over the general or basic stereochemical principles. This will be including chirality, prochirality, asymmetric synthesis, aldol condensation. These points as applied to aldol condensation, Sharpness asymmetric synthesis, and Negishi reaction, to name a few, though there are many name reactions. Now, as we all know, what's the essential criteria for a molecule to be chiral? Well, there shouldn't be any symmetry, it should be dissymmetric. And the carbon in the molecule, when it's attached to four different groups, naturally it is asymmetric. But when there are more than one carbons, in that case, we have to also see as to whether this is missing, that is the plane of symmetry. If it is present, like in this case, it will be achiral. Here there is no plane of symmetry, no axis of symmetry. In that case, this will be chiral. And if it is chiral, whether there are one carbon, two carbons, or multiple carbons, then it is optically active, as we all know. Moreover, the chiral carbon, the absolute configuration or the arrangement of atoms or groups in space can be designated by the absolute configuration, which follows, which is the CIP nomenclature or Kahn and Gold prologue. According to that, the groups which are attached, they are numbered according to their atomic number, from the highest, going from the highest to the lowest. And if it is the three-dimensional projection in the wedge form, in that case, the atom of the, or the group of the lowest priority, should be away from us. And now going from OH, the highest priority, to CH3, second priority, OH, the first priority, ET, C2H5. Now this is two carbons, okay? So this is one carbon. So this will be the second priority, ethyl. Second priority, and CH3, the third. The direction, as we view these groups, now mind you, this is not the direction of optical rotation. We are viewing the groups in this direction. So it is clockwise. Hence, the absolute configuration is R. When viewed in the Fisher projection, how do we write this as a Fisher projection? Is because the groups in the along this in the same plane are put along the vertical line, and those which are out of the plane of the paper, that is the wedge and the dash, they are placed along the horizontal line. Now, along the horizontal line, when they are placed, in that case, as we can see, because OH and CH3 are here, so H and C2H5 along the horizontal plane will be such that this group is towards this right and C2H5 is towards the left. Why? Because OH and CH3, they are pointing towards the left. So when they are pointing towards the left, in that case, the group on the wedge is also placed on the left. Had the opening been towards the right, in that case, we would have placed this C2H5 on the right. So this is along the wedge placed on the left, because OH and CH3 are along the left hand side. So this broad line along the left. And as we can see, once again, 1, 2, 3. The direction comes anti-clockwise, but because H is along the horizontal line, so automatically it will be reversed according to CIP principle. So hence it will be the R configuration. Now there are certain principles that rotation by 180 is allowed, rotation by 90 is not allowed, rotation by 180 along the plane of the paper. Along 90 is not allowed, because in that case, if along 90, we will get the other enantiomer. Enantiomer result then, because if we swap left and right bonds, if we just exchange these two bonds, we will be getting the enantiomer of this. For example, if ET and H, ethyl is placed here, H is placed here. In that case, we will be getting 1, 2, 3, right hand side direction, clockwise, but since the group of lowest priority is along the wedge, so we reverse whatever we see. So it will be the S enantiomer. Now, meso compounds can be seen by the symmetry. As we all know, besides the chiral carbon, chirality also depends on the chiral axis. Why is the axis here chiral? How can we view? Because this is sp hybridized. Sp hybridized means that there are two unhybridized p orbitals which are orthogonal to each other. In order to form a bond with this terminal and this terminal carbon atom, what will happen? These two, again, since this will be having the two orthogonal or 90 degrees p orbitals, automatically it will happen that one terminal will be having groups along the same plane while the other will be moving out of the plane. In that case, this assumes the shape of an elongated tetrahedron. These two groups in the same plane and this out of the plane. The CIP nomenclature in this case, as we all know, is slightly modified because if we view it depending from which direction, this is pentadiene. So in order to see what type of an isomer this is, R or S, what do we do? Since we are viewing it this time from the left hand side, so the groups on the left hand side, irrespective of the atomic number, are given priority. Left hand side means CH3 and H, because these are the groups which should be put on the horizontal line. And since we are viewing it from the left hand side, so H will be placed on the left hand side, the group which is away from us, so on the left hand side. And these two groups are placed as we see them, north and south, north and south. Now, since we are viewing it from the left hand side, so the left axis, this left side axis, this will get priority. We've shown it by this broad line. Getting the priority, this will be A, number 1, this will be B, number 2, this will be C, and this will be D. In this case, the direction of rotation hence is clockwise, so this is the R isomer. This is a cumulene. In other words, there are two double bonds this time. We can't visualize a carbon with, we can't visualize this as having showing optical isomerism, but this does show because of the chiral axis, because the central carbon atom is sp hybridized. Had there been an odd number of double bonds, in that case we would have got geometrical isomers rather than optical isomers, as we all know. Similar is the case chiral axis in the case of biphenyls. Similarly, biphenyls, because these two phenyl rings will be in one plane as long as there are no ortho substituents. But as soon as ortho substituents are attached to them, suitable heavy ortho substituents, what will happen? In the same plane, there will be so much of steric crowding that automatically one of the phenyl rings will tend to move in the other direction by carbon-carbon single bond rotation. So these two bonds, because along the same plane, they will just too much of crowding, they will create too much of steric hindrance. So this moves away. This moves away, so automatically one carbon goes back, one of the groups, and the other moves towards us. Now this is again the case of an elongated chiral axis, and of course the RS nomenclature, absolute configuration, is taken out as it is for the case of allenes. If we view it from this side, this side now has what? The groups out of the plane, so we'll give this axis priority. And if we are viewing it from the right hand side, the group away from us will be placed on the right hand side. So first, second, then third and fourth, as we see them, the direction comes anti-clockwise. Whether we view it from the right hand side or the left hand side, the absolute configuration will be the same. In this case, when we are viewing it from the left hand side, because the groups are in the same plane, so we place them in the vertical line and give this axis the priority. So 1, 2, after that, viewing it from the left hand side, so the group which is away from us will be placed on the left hand side. So 1, 2, and then this is 3 and this is 4. So going from 1 to 2 to 3, the direction comes again anti-clockwise. Here it is irrespective whether fourth priority groups is present on the vertical or the horizontal line. Here the axis is given priority. Similarly, this is planar chirality. Planar because this is benzene in one plane, but if it is got heteroatoms at the end, this is like a handle, and if it is attached to methylene groups in a cycle, and number of n should not be more than 8, otherwise this becomes very large and this ring will be easily able to flip in and out. And if it is substituted at the ortho position by a bulky group, then on rotation along this carbon oxygen single bond, this Br will not be able to slip and change into its mirror image. Hence, this will show optical activity. So it seems as the entire plane is optically active. Such chiral compounds are known as ANSA compound, ANSA or handle. Similarly, here this is a simple paracyclophane where there is no oxygen but there are methylene groups. This is CH2N. At the same time, this can also be another benzene ring. In this case, a pilot atom is selected. Pilot atom should be away or out of the plane of this ring. So this is and it should be on the same side as the substituent. So this is the pilot atom. From that, we just select the atoms as they come. So carbon number 1, 2, 3, the direction is clockwise, hence this is R. Let's see in this answer compounds. Here, this is the substituent, so the pilot atom will be selected from this direction in this case. So this is the pilot atom going from the pilot atom 1, 2, 3. This is again the R isomer. Coming to another term before we move on to our reactions is prochirality. Now what is pro? Pro means favoring. In this case, no chirality is seen in the compound, but it has certain homomorphic ligands, that is ligands which are similar, a pair of such similar ligands. When they are substituted one by one, then they give rise to chiral compounds. So this compound or this molecule is said to be prochiral, that is favoring chirality on substitution if it has a double bond, then in case by addition. Now again, we can name them as pro-R or pro-S, these homomorphic ligands, depending upon whether we are getting an R isomer or an S isomer. Let us see in this case if these hydrogens homomorphic, similar ligands, similar in all respects. If one by one, this is replaced, the one in the wedge, by deuterium. So the priority will be 1, then 2, then 3, clockwise. So hence, this is pro-R. Let's see this other one which is on the dash. If this is replaced by deuterium, 2H, deuterium, the heavy hydrogen, then in this case again priority 1, 2, 3. But since the group of least priority is not present along the dash, that is away from us, so though it is clockwise, but we will reverse it because it is not following the CIP rule. Hence, this will be the S isomer. So this hydrogen is pro-R, this is pro-S. Once we know prochirality, so this is again enantiotopic. So these two hydrogens are enantiotopic in this case, CH3, CH2OH. This is ethanol. These are enantiotopic because their replacement gives us a pair of enantiomers or mirror image. One is S and the other is R. Similar is the case in this where we are replacing first HA and getting this. Here, this was not optically active, but when we replaced HA, then automatically this became dissymmetric. So number 1, then number 2 priority, this entire group. Number 3, direction of rotation is anti-clockwise. So this is S. On replacement of HB, now in this case they are present on different carbons, but they are homomorphic, these two hydrogens. When we replace HB, on replacement of HB by Cl, we will get then what? First priority, then second priority, then third priority. The direction comes what? Clockwise. So this is R. In other words, HA and HB again form a pair of enantiotopic ligands. Topicity describes the relationship it has with the rest of the molecule, because an atom when sp3 hybridized may have prochiral center. When on replacement of one of the groups, one by one, we get a pair of enantiomers. Similar is the case of R double bond. See, this is RCHO, an aldehyde. This is a double bond. How is it prochiral? It is prochiral because if we reduce it, for example, or if we well, on reduction, this will be hydrogen, there will be another hydrogen. But if we react it with, for example, another nucleophile, such as Grignard reagent, on addition, so CH3 will come And here we will get OH, Grignard reagent, carbonyl, so it will give us an alcohol. What will happen? This attack can be either from the re side. In this case, rather than pro R and pro S, we call them the re and the psi phases. This is the re phase. And now going from, again, priority is named in the same direction. 1, 2, 3, clockwise direction. So the re phase. Here, if it is the re phase in this direction, then below this phase, the other side will be the psi phase. Above is the re phase, then the other side will be the psi phase. So what do we do with the basic knowledge of all these concepts which you must have studied earlier in your MSc classes? Why, we move on to the important concept of asymmetric synthesis and then our name reactions. What is asymmetric synthesis? Is when we are trying to synthesize a chiral compound from a compound which does not have any sort of, or we are trying to synthesize a stereoisomer from some compound which itself is not a stereoisomer. So what are the conditions which are required? The conditions which are required for asymmetric synthesis are, first of all, that there should be the presence of a pro-chiral unit. The pro-chiral unit should be present in enantiotopic or distereotopic. They can be groups or they can be phases. At the same time, there should be asymmetric induction. Asymmetric induction implies stereoselectivity. If we get the R and the S form in equal forms, then it is not asymmetric synthesis. Of course, we are synthesizing chiral compounds, but we will be getting a racemic mixture. So that won't be asymmetric synthesis. Only when there is a stereoselectivity, that is one isomer is formed in excess over the other, then we say asymmetric synthesis is taking place. And it's very important because we need pure compounds. They can be enantio selective, it can be diastereoselective, but since these compounds show different physiological activity, the stereoisomers, so it is very important from the synthesis point of view. Let us see stereoselectivity, enantiotopic or diastereotopic presence of these groups and how we can apply these principles to our different named reactions. So first of all, we will move towards aldol condensation. Now we all know what aldol condensation is. Since previous classes we've been studying when carbonyl compounds, and they can be two aldehydes, they can be aldehyde or a ketone, they condense together to give us a new carbon-carbon bond with the functional groups carbonyl at one end and OH at the other. It is known as aldol condensation. So acid or base catalyzed. Now what will happen in the presence of this, if, see, this is a ketone, this is an aldehyde, so this is R1 CH2 C double bond O. What exactly transpired was in the presence of a base, because we all know C double bond O carbonyl, the alpha hydrogen which is present is acidic in nature. Why? Because C double bond O is pulling electrons towards itself. So this carbon gets a positive charge. It pulls electrons from the next carbon, which in the presence of a base will lose H positive. So the electrons will come here and we get a carbene ion, which is stabilized by forming carbene ion here. So it is pulled towards the oxygen. Electromeric shift, O negative here, stabilized by either lithium, selenial, cellulyl ethers or borates nowadays, and we will get this enolate. O negative, Li positive, enolate. Enolate, because a double bond has been created, so geometrical isomerism or diastereoisomerism comes into the scene. It can be Z or it can be E-enolate. Why is this Z double bond? Because see, first priority, then this R second priority along this. Then this R first priority, H second priority. Since similar priority groups are on the same side, this is Z-enolate, which has been produced by this ketone in the presence of a base. Enol has been produced, stabilized, forming enolate. This enolate will give us on hydrolysis a syn plus minus pair. How? syn. When this condenses, and this will condense with this this is C positive, O negative. So C positive will attack this electron pair, and a new carbon-carbon bond will be formed between this carbon, which has this R1 attached to it, R1, and here we will get, this is R1, and here there is R2, at the other end is the R2. So R1 here will condense with this carbon, forming another new bond with C positive. So this will be C positive, C R O negative, which will form OH. So we will get a syn plus minus pair if it is a Z enolate. Plus minus because this will be having, this aldol will be having a mirror image. Similarly, E enolate. If Z enolate is formed, at the same time, the other diastereomer, E enolate, can also be formed. Why E? Because 1, 2, priority along the double bond on this carbon, then along this carbon, 1, hydrogen is 2. As we can see, groups of similar priority are opposite sides, so this is E enolate. E enolate, through mechanism, we know forms an anti. It will form an anti-aldol. Z will form a syn aldol, and this will form anti, because a new chiral center has been generated, as we can see here, COH, COH. So why this is now anti, these two groups are anti to one another. Prior to this, this was not chiral, nor was there any chirality over here, because this is RCH2. Now you can see these two centers, two new centers have been generated. Hence, carbon number to the power of 2 chiral centers, 2 to the power of 2, we will get 4 stereoisomers. This is syn plus minus pair. This is anti plus minus pair. Plus minus indicates RS. This is shown by the optical rotation. So this is one pair, racemic. This is one pair. So this is aldol condensation which is taking place. So how can we control it, the aldol condensation? What can we do so that we get one isomer in preference over the other? So by using dibutyl boron trifluoromethane, this is dibutyl boron trifluoromethane, sulfonate, that is known as trifluate. This trifluate is used in the presence of a base. In the presence of a base, this is a base, what will happen? Base, from this alpha carbon, this will extract a H positive. So we get a carbene ion. And this carbene ion, hence, this negative charge move here. Oxygen pulls this pi electrons here. And this, together with this triflate, is stabilized and we get an enolate. En, because this double bond moves here, and these pi electrons, this electron pair moves here to the carbene ion which has been formed, and this moves here. So here we will get an enolate stabilized by triflate. And this, why we are using this rather than silyl or lithium? Why to enolate? Because oxygen boron bond is very short. So we will be easily able to, there'll be a lot of steric crowding, as we will see in the intermediate transition state. So we can easily separate E from the Z. We will be separating E from the Z. How? See, this is what type? Now, this is enolate oxygen number 1 priority, then this is number 2 priority. This is number 1 priority, and what is not shown here is a hydrogen, automatically is 2 priority. So this is the Z enolate which is formed, and this on condensing with R1CHO, the aldehyde, nucleophilic here, R1C, this will get a positive charge, so it will attack this electron pair over here, pull this towards itself, and a new carbon-carbon bond and 2 chiral centers will be generated. So R1C, C, H, OH attaches with the C, carrying this R2, a new bond has been formed and 2 chiral centers. And since we are using boron over here, this triflate, so we will get in this case sin as the major, more than 97%, and anti as the minor. How is this possible that we get sin as the major and this anti as the minor? Well, this is possible, as we can see, by showing our entire mechanism by using Zimmermann-Traxler model. Now, this is Z enolate. Z enolate at the same time E enolate is also formed. Okay. Besides Z, we also get E enolate. Both are formed. And the two we can easily separate by means of our column chromatography. So we have separated, and Z moreover is separated, formed in excess, as we saw here. This Z which is formed, this Z isomer, because here R3 and H, they are on the same side. Had it been the E isomer, in that case R3 and R2 would have been on the same side here, and H would have been here. So there would have been a lot of crowding. Hence, this is more stable, can be easily separated. And this gives rise to the sin. Why the sin? We will see, taking this Z enolate. Z enolate, you all know, double bond. Now priority number 1, number 2. Priority number 1, number 2. So see, this hydrogen is on this side, so it does not create steric crowding with R3. Hence Z enolate is more stable in comparison to the E. If R2 would have been on this side, then these two would have created a steric hindrance, and so that would be the minor product. Now this Z enolate, which is major, is separated, and if when this reacts with R1CHO, that is the aldehyde, these are the transition states with Z enolate which are formed. Now, showing the Zimmermann-Traxler model, we are all familiar with cyclohexane, the chair form. So this is R2CH double bond CO Br2, and this R1CHO can approach this carbon because it requires electrons, because electrons are being pulled towards oxygen. So this carbon becomes positively charged, it attracts this pi bond. It can do so in such a way so that, R1 and R3, they are along the same side. How? We can see carbon number 1, number 2, number 3. When 1, 3 are diaxial in cyclohexane, then they are cis. Then they are cis. Here they are cis. Lot of crowding. So energy of the system will increase. And when this will form a bond with this, taking the electron pair, the product, it will be formed because this carbon and this carbon has R2. This is where we can see on the axial. This is R1 on the axial. So the new bond which will be formed will be again, because R1, R2 diaxial, or we can compare by these two hydrogens, these are di-equatorial. So the product which will be formed, this carbon and this carbon, will also be having the groups attached to these two carbons as anti, because di-equatorial or diaxial are anti to each other. So the product will be formed R1C, R1CH, OH. This will be anti to this other group R2, which is attached on this carbon. Hence, an anti product will be formed. But because R1 and R2, that is 1 and 3, they are on the same side, lot of crowding, hence this will be less stable as compared to this other transition state, where again by Zimmermann-Traxler model we can see that when R1CHO, it can approach it in such a way so that R1 is upwards rather than being downwards. This R1 is upwards, hence 1, 2, 3. Here R3 and H are on the same side, so there will not be any steric crowding. So such a Zimmermann-Traxler model, the transition state will be stable, and the product will be, which will be formed from this, because here as we can see, R1 and R2 are axial equatorial. 1, 2 axial equatorial means a cis product. Here H and H, this is equatorial, this H is axial. It is cis. Hence the product will be formed, OH along these two carbons because this new bond is being created. So it will be R1, R1, C, OH, C, the new bond this is formed, and R2. So these two, R2 and OH, along this carbon bond which has been formed, will also be cis to each other or syn to each other. And this will be the major product. So what have we done? By using this and separating the Z form which is more stable by using our dibutyl boron trifluoromethane sulfonate triflate, we have been able to isolate syn firstly as the major product. From syn, we here syn the major product. Why? Before forming syn as the major product, we isolated Z enolate, which again is the major, since these bonds are short between oxygen and boron, and so this will be shortened, so there will be less crowding in the Z form rather than the other form of the enolate, which will be the E form. So we have done double asymmetric synthesis because first we separated Z as the major form, and then from Z we got syn as the major. So this is, we are controlling the reaction by this method. So this is known as directed aldol condensation. And since out of these two, because these two as we can see are, these two are distereomers, okay, not enantiomers. Enantiomers, if both these are wedge, these two would have been both dashes, then it is an enantiomer. So we are able to separate the syn from the anti. So distereoselectivity. Now after distereoselectivity, let us move on to this directed aldol condensation regioselectivity, because we should also know that how is regioselectivity different from distereo or enantio selectivity. Regio means that the attachments of the product we get, they are placed on not the same carbon, but structurally they are different, the two forms. How? Let us see by taking an example of 2-pentanone. 2-pentanone has two alpha hydrogens, this side and this side. This side is crowded because it has another CH2, whereas this side is free. So in the presence of a small base such as OH, it can withdraw an H positive either from this carbon or from this. This carbon, since has no bulky groups attached here, no carbon, so this will be kinetically favored. So this is the kinetic enolate. Easily we can get carbon negative by losing H positive. Kinetic enolate will be formed here. From here, this double bond, this O negative here, kinetic enolate. This will condense with an aldehyde to give us this type of an enol, this type of an aldol. On the other hand, if this OH withdraws an H positive from this alpha carbon, we will get an electron pair H here. So the enol that will be formed in this case will be such that this will move here, this oxygen here, and this double bond will come here. This is the enol, and this is, between those two carbon atoms. The double bond is situated between the more substituted carbon atoms, unlike this terminal one. So this, though this is kinetically favored, this will be thermodynamically favored energy wise. So this is a thermodynamic enolate, and hence this will be formed more because energetically favored, and this will give us this type of a product. So this will be the major product. Supposing if we want to synthesize a compound of this type, because it is maybe important from the kinetic product is important from the point of view of a biologically active compound or some medicinal or pharmaceutical compound, how do we synthesize the kinetic product as the major? Well, we are trying to guide. As you can see here, the connectivities are different. Hence, these are not stereo, but these are regioisomers, because here the condensation has taken place between this carbon, whereas in this case, the condensation has taken place between this terminal carbon. So we are trying to synthesize this product. So how do we control the reaction? We are now directing it as we did earlier in distereoselectivity. Here we are directing it how? We choose a heavy base like LDL, lithium diisopropylamide, bulky base. The bulky base will not be able to attack at this position. So it can only be able to extract an H positive from this end. So the kinetic enolate this time will be the major product, leading to the kinetic enolate leading to the kinetic product being the major rather than the thermodynamic product. So this is, since we are directing, we are controlling the reaction. So this is directed aldol condensation leading to kinetic enolate as the major product. And this is termed as regioselectivity, unlike stereoselectivity. But now at the same time, we can also get, as we talked earlier, that we had either of the two forms as major. We got syn as the major product. Now how to separate it further? Because the syn will also be having, syn form will also be having its different enantiomer. Syn will be having an enantiomer, that is a mirror image. So how to separate the enantiomers one from the other? First we have done distereoselectivity. Now we will do enantio selectivity. And this enantio selectivity is done how? By a very interesting method, that is, we are using, going again for double asymmetric synthesis. Why? In this case, when one of the components of the Aldol condensation is optically active, then enantio selectivity can be done. So what do we do? So we introduce a chiral auxiliary. Now chiral auxiliary, that is, this is from, valine. Valine is an amino acid. From valine, this was over here CH3CO, CH2, CH3. This is made to condense with the aldehyde. So when this is made to condense, this chiral auxiliary at one end, at CH3, here there was a CH3. Okay, so this was over here, C double bond, this was attached here. When this is attached here at this end, what will happen? CO, and this is attached here with N, 1, 2, 3, C double bond O, CH2, CH3. When this will combine, then in that case, because this is chiral, this amino acid which has been attached at this end, this is chiral. So what will happen? This chiral auxiliary again, it is just guiding. This will attach in such a way from one side, so it creates a hindrance. On creating a hindrance, what will happen? When we form an enolate in the presence of a base and aldol condensation, then this aldol will be formed, or this condensation will occur, because this is a big molecule is causing, this is chiral, so it will project in such a way that this attack, nucleophilic attack on this, can take place only from one direction. Hence, this on hydrolysis will give us, of the syn product, we will get only one enantiomer. Only one enantiomer will be formed rather than both the enantiomers. So this is called as enantio selectivity, because out of the two forms, this is dash 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 dash, these two chiral centers. The mirror image will be both CH3 and OH on the wedge side, the other mirror image. So by using a chiral auxiliary at one end, attaching it to one end, and this chiral auxiliary on hydrolysis can be easily removed. This will be easily removed from this terminal. So here we get CO, CCH3, CO on hydrolysis. This was removed from here, N, and we NH in the form of NH. And here we got, so here is NH2 hydrolysis, here OH at this end, OH and an H. This is removed on hydrolysis. The function of the chiral auxiliary is, because it is chiral, so three-dimensionally it projects itself in such a way that the attack or the formation of the new bond can only take place from one side. So this is CO, C, CO here, C. The C will be the one which will be forming what? Here, C at this end, CH2, CH3. This will be forming the carbene ion. So the enol which will be formed will be such that can attack this RCH O R1 CHO only from one surface, giving rise to only one type of an enantiomer of syn double asymmetric synthesis. Now let's move on to another very important reaction, and this important name reaction is Sharpness Asymmetric Epoxidation, whereby allylic alcohols, they are converted into epoxy alcohols. And why this is important is because these epoxy alcohols are very reactive and they can be changed into a number of very useful products by way of pharmacy, by way of bioactive molecules, or other products which are used for further synthesis. For this Sharpless, Katsuki and T and KB Sharpless, they have this published in Journal of American Chemical Society in the year 1985, and for this he was awarded the Nobel Prize in 2001. This reaction is both chemoselective as well as stereoselective. We will see how. Here, chemoselective implies that though there may be a number of double bonds, but only the double bond which is only that OH groups which is allylic. Number of double bonds are present and maybe many OH groups are present in that molecule. But that alcohol or the OH, only when this is allylic, that is CH, CH, CH2OH, only then it forms an epoxide. Otherwise, the other OHs, they might be present elsewhere, double bonds might be present, but until and unless it is an allylic alcohol, it won't form an epoxide. Hence, this is highly chemoselective. And at the same time, it is also stereoselective, and we get enantiomeric excess more than 90%, that either of the two forms is formed, because now see, this is a double bond, so it will have two faces, the psi phase or the re phase. So we can get an oxygen above this plane of paper, on this along this plane of paper, above or below this plane of paper. Both type of isomers can be formed, and this is highly enantioselective. So how does this epoxidation occur? This occurs by using diethyl tartrate and TBHP. TBHP is used to basically introduce the epoxide group. TBHP is used for introducing this, which is tertiary butyl hydroperoxide, TBHP, tertiary butyl hydroperoxide. So, and at the same time, the catalyst which is used is titanium isopropoxide. Titanium, here this is the one which is the catalyst. So displacement of isopropoxide ligand on titanium by DT, TBHP, and this, because this diethyl tartrate, as we can see, it can be minus or plus, that is, it is chiral. So we get a chiral epoxide, one of these two in excess. It can be either this or it can be either this. In other words, this was not a chiral phase, but it became chiral. This is not chiral, but it is a prochiral phase. Prochiral, that means prochiral phase, and there's this chiral influence by diethyl tartrate in the presence of this catalyst will lead to either of these two enantiomers in excess. In other words, asymmetric induction or stereoselectivity has occurred. Therefore, by using either minus or plus, we will know exactly what type of a product can be formed. So this reaction is also stereo specific. Let us see with the help of a few examples. Now, C double bond C, CH2OH. So this is the allylic alcohol. On Sharpless epoxidation, this phase, if we see, and we just determine whether it is a psi phase or a re phase. So let us see carbon double bond carbon. So this carbon is attached to C, which in turn is attached to O. So this gets the first priority. This carbon double bond. So this carbon is attached to another carbon. So this is second. And this here is attached to hydrogen. So this is third priority. Moving on the plane of the paper, along the plane of the paper, 1 to 2 to 3 gives us what direction? The direction which is given is anti-clockwise or anti-clockwise. Anti-clockwise means what type of a phase is this? This is the psi phase. But here for sharpless, we are using dimethyl tartrate, DMT. DMT can be used, DET can also be used. Here diethyl tartrate, DMT, dimethyl tartrate, or DIPT, diisopropyl tartrate. Here we are using plus. And the plus DMT, which is chiral, it guides the oxygen in such a way from the epoxide that oxygen is delivered by plus DMT on the resurface because it protects one side. Along one side it aligns. So it is delivered the oxygen from the re phase. As we can see, this phase 1 to 2 to 3 anticlockwise. So along the plane of the paper, this is what? This is the psi phase. So in other words, oxygen will be delivered below the plane of the paper. Below the plane of the paper. So this will be the product or the epoxide that is formed. Now let us see Sharpless in this case. Allyl alcohols CH, CH, CH2OH. Now fixing the priority along this phase, which is a prochiral phase, moving from 1, this is number 2 carbon carbon, this is CuNO number 1, 2, and over here number 3 because this is CH3. On Sharpless, if plus DMT is being used, we know plus DMT or plus DET, either of these can be used, it leads to a delivery of the oxygen forming a re-epoxide. So if this is the along the plane of the paper, this is the psi phase 1, 2, 3 anticlockwise. So again oxygen will be delivered below the plane of the paper. So this will be the product and the yield is 45% and enantiomeric excess is 95%. Just imagine such a good asymmetric synthesis forming this epoxide, and this is used in as a for methocyanin sign intermediate, an important drug. Similarly, Sharpness epoxidation in this case, when this is the alcohol CH, CH, CH2OH. Let's see by numbering. So this is 1, this is 2, this is 3, again anti-clockwise, and this time minus DIPT is being used. Minus DIPT delivers the oxygen, guides it towards the psi side. So as we can see, this is the psi side along the plane of the paper. So this time the oxygen will be delivered along the plane of the paper, not below the plane of the paper, but here the same side on the same plane of the above the plane of the paper, above the plane of the paper. 1, 2, 3. This is psi, and minus DPT also DIPT also guides the oxygen, makes it delivers towards the psi side. Minus DET psi side. Minus DET can also be written as SSDET or DDET. Plus DET can also be written as RRDET or LDET. So we get this as the epoxide, 58% yield and 95% enantiomeric excess. And this is used as an erythromycin intermediate. We all have heard of erythromycin during COVID times. Now let us come to the third synthesis here. In this, we can again by fixing priority, C with an O first priority, C with another C second priority, and here C at this end, this is just an H, nothing written, so an H over here along this bond. So third priority. This is which direction? Again, anti-clockwise, or this is the psi phase along the plane of the paper. And since we are using plus DPT, which delivers the oxygen or the from TBHP along the re phase. So if on the plane of the paper is the psi phase, so the re phase must be present below the plane of the paper. So it will deliver the oxygen below the plane of the paper as shown it by dash. This will be the product, 80% yield and 95% enantiomeric excess. Leukotriene, another important biologically important pharmaceutical compound for that, and intermediate. So these were the examples for Sharpless asymmetric synthesis, this important reaction, name reaction. Now let's move on to this very interesting example which was given in one of the exams. So see, this is carbon cyclohexane, carbon double bond O, CH3, CH3. And as we can see with this phosphorus, what will be formed? This indicates a Wittig reaction. Wittig reaction, how? Because NaH base is used, this will pull, because phosphorus here 1, 2, 3, 4, positive charge, all the valencies are not there. So this positive charge, so this carbon, the alpha hydrogen will be acidic. So this will pull H positive. We get a carbene ion. In other words, a yellide, phosphorus yellide has been formed by means of NaH. So let us see the product which is formed after this, because Wittig reaction indicates that the CH will introduce itself. This P double bond O will be removed. I won't be repeating this Wittig reaction. I've given it in a number of name reactions earlier in my lectures. So we will get CH over here. And since this yellide which is formed is a stable yellide, so the stable yellide will lead to a trans product, as we will see in the reaction mechanism here, which I have indicated. So this was the compound. What happened through the Wittig reaction? C double bond C, C double bond C. PO. This was pulled oxygen and through transition state, butane, and we got C double bond C. And C double bond C, because this is a stabilized halide. Why stabilized? Because when the negative charge carbene ion will be formed here, we have got this over here, COOET, which pulls this carbon negative charge and stabilizes it. So such a halide is known as a stable halide, and a stable halide also always leads to a transalkene. So this transalkene will be formed. Trans, we can very well see this is trans along the double bond. Transalkene is formed with priorities. We can fix 1, 2. This is 1, 2. So transalkene is formed, which on reduction, because this has got COOET, the ester group, COOET, CH, COOET over here. So with lithium aluminum hydride, which is specific for this carbonyl, this ester linkage here, it will reduce it to an alcohol. So we get an allyl alcohol. C double bond C, CH. Yes, this is C double bond CH, CH2OH, allyl alcohol, which by TBHP, titanium and minus DET. Now we know that minus DET throws or adds or forms the epoxide from which? From the psi end. So let us see what is this end over here, counting it one by one. If this end over here, this is carbon attached to, because here this is carbon, CH2OH. So C with an O, the first priority. This is the face, chiral face double bond. This is first priority. Then over here, this carbon here attached to these carbons, second priority, then hydrogen. And this face above the plane of the paper is the psi face. Since minus DET is being used, it forms the epoxide, guides it towards the psi phase or the anti-clockwise, and along the plane of the paper is the psi phase. So along the plane of the paper, it won't be this time by dash below the plane of the paper. This is above the plane of the paper. Here we get this epoxide, or this will be the product that will be formed. This is Wittig reaction followed by Sharpness Epoxidation. Now moving on to palladium catalyzed cross coupling reactions. Now this is why I took this reaction up, because prior to this there is of course the other reactions, the Heck and the Sonogashira reactions. The number of still reactions, they are all of them are catalyzed, palladium catalyzed cross coupling, where new carbon carbon bonds are generated. And for this, Negishi got the Nobel Prize together with Heck and Suzuki in the year 2010, because by using such a reaction, new carbon carbon bonds were formed, the cross coupling reaction took place. So this is the reaction which is written in general: Rx plus R dash ZnX dash, palladium catalyst, and R and R dash, they beautifully couple with each other, and new carbon carbon bonds are generated. Very important compounds here. X can be BRI triflate, R can be aryl alkyl alkynyl or propargyl, X dash can be X dash here, can be ClBRI, and R dash can be alkyne aryl allyl alkyl homoallyl homopropargyl. M is equal to PD or Ni. Generally, palladium is used. The ligands which are used together with this can be triphenylphosphine, BNAP 2,2-bis diphenylphosphine, or at the same time DPPE, that is 1,2-bis diphenylphosphinoethane. Now, how does this reaction occur? These are all mechanisms which are similar, or palladium catalyzed are similar to one another. This is the palladium in the zero state. The zero state palladium changes into the +2 state by oxidative addition with this aryl or alkyl or alkanyl halide. Oxidative addition, why? At one end of PD we get R, at the other end of PD we get X. So zero state changes to +2. PD, R and X. And this by transmetallation. That's the beauty of Negishi reaction, because here zinc is being used to transfer this R group from zinc to palladium. So transmetallation R1ZnX, and since zinc is, more environment friendly as compared to others, tin, etc., which have been used. So hence, this is a very important reaction. So R1 from here, zinc, is transferred to PD. So this is PD, L, till here it was R. See, R was attached here prior in oxidative addition. Now zinc transferred this R1 here and took the X from here. The X was replaced by R1. So this is transmetallation. R moving from one metal towards the other, that is palladium, and at the same time Z and X1 and X. This is formed as the byproduct. Now, when this is formed, see over here, this undergoes cis trans isomerization and by reductive elimination, because by reductive, just the opposite of oxidative addition is reductive elimination. Now, the valency of palladium, once again from the second, it moves on to the oxidation number also reduces, the valency also reduces to the state 0, PdL2. This is formed, and R and R1, this coupled to each other because they are present on the same side R and R1, they by means of reductive elimination. In doing so, this valency and this valency of palladium is curtailed. So hence from PD2 it changes to PD0, and R1 and R coupled to give us this product R1, the cross coupled product, and new linkage has been formed, carbon-carbon bonds. A very, very important reaction by way of synthesis of many important compounds, the Negishi reaction. Now, why this Negishi reaction I am discussing here is because we will just be doing one or two examples by way of its mechanism and stereochemistry. Why? Because the Heck reaction is similar in all aspects to our Negishi reaction, which we discussed. This was later on work, 2010. Heck started it very much earlier. They were working side by side, Negishi, Heck, Suzuki still. So Suzuki, Negishi and Heck were awarded the Nobel Prize in 2010. That is why I have mentioned this reaction here. They are all similar as far as the mechanism goes. They follow the same pathway, oxidative addition, where palladium 0 is changed to a higher oxidation state. And then after that, it is the formation of this further by reductive elimination, the product. So similar cycle takes place in the case of Heck reaction. So this is the Heck reaction, except here we have this allyl iodide. Zinc is not present, unlike it was present over there for transmetallation. And the allyl halide and this double bond, they are present in the same molecule. Same molecule. Otherwise, generally what happens, the allyl iodide is present at one place and this double bond is present in the other molecule. And then the coupling takes place. But here, since both these are present in the same and palladium catalyst is being used in the presence of a base and AgCO3, this indicates a Heck reaction. What will happen in the presence of a base and palladium is that PD, again by oxidative addition. So PD, it has got these two ligands. It will, by oxidative addition along this, will add to this double bond at one end and this iodide at the other. So PD with this carbon, double bonded carbon, this double bonded carbon, here we get PD, at the other end we will get this I. So oxidative addition, as we can see, valency of PD has increased. So this iodide has moved to palladium and in place of iodide, a new linkage with carbon. So palladium is forming two bonds, one with this unsaturated carbon and the other end with this iodide. So oxidative addition. Now what will happen after this will be in syn insertion. The insertion is always syn. Syn insertion implies that in the next step, what will happen is this double bond is present over here. Along this double bond, what will happen is this palladium and this carbon, unsaturated carbon here will insert. How? Syn means from the same side, and that is the reason why this wedge is being shown here. Wedge means towards us, the CN is towards us, and syn will be that both the bonds will attach along this double bonds. This is the double bond, and when this carbon attaches here and this palladium attaches here, they will do so by a syn, means they will be on the same side. Now, if this Cn is towards us, that means this CC bond will be away from us. This is towards us. This is a cyclohexane ring. So this is towards us. This will be away from us. So if this carbon forms a bond with this carbon, because now a cyclopentane ring has been formed here, so it should be such that this carbon-carbon bond and this carbon-carbon bond should be on the same side. If this is dash along dash, because this Cn is along the wedge, so this CNC will be along the dash. So this should also be present away from us or along the dash. Otherwise, if this is away from us, but this will be towards us, no ring will be formed. So in order to form a cyclopentane ring, this carbon will form a bond, break away from this PD. This will form a bond with this carbon away from us. And this carbon is also away from us. So they are all both on the away from us from this on the same side. And hence a cyclopentane ring will be formed here. Now this other carbon, this PD will migrate to this carbon. One electron with this carbon over here, one bond here, and one bond with this PD. Now this PD, since the addition always takes place syn, that is if this is away from us, so this PD with the L and the I, this also should be away from us as shown by the dash. After this, reductive beta hydride elimination will take place. The elimination, and that elimination is also syn. How will it be syn? It will be syn because see, now this is dash and this hydrogen present here, because this is dash, this is wedge. So it means this hydrogen and this are not on the same side. So they are anti. So this hydrogen can't be eliminated as Hi in order to the H negative. On the other hand, here this CH2 here has two hydrogen, one along the same side and one on the opposite side as is seen by the dash and the wedge. So here this PD along with this H negative here, H will migrate from here, hydride H negative. H negative migrates from here, and this bond is left here. The double bond is created, and this double bond now this time, as we can see, is present along the less substituted carbon. Generally what happens, people draw the product by hydride elimination as this, because this is the more substituted carbon, as this. No, because of this mechanism, syn insertion and syn beta hydride elimination, we will get the less substituted product as the major product in this Heck reaction. This is the Heck reaction. Similarly, if we see this reaction, Rx plus CH2, CH, CH2OH, palladium catalyzed. What is the product? So again, in the presence of palladium catalyst, there will be syn insertion. Along this double bond, there will be syn insertion, PD, R, palladium, first oxidative addition. That is along palladium at one end, R is added, at the other, X, and two new bonds are formed. So oxidative addition. Now, along this double bond, there will be syn insertion. So syn insertion at one end, R will be inserted, as was shown earlier, and the other end, PD will be inserted. So if R is inserted here, PD at the other side, R at one end of the double bond, PD at the other, again the insertion is syn. After syn insertion, there will be beta hydride elimination, and the elimination also takes place in a syn way. Now this has two such, because this is CH2. So if one hydrogen is away, the other will be towards palladium. Similarly, if here one hydrogen is away, the other will be towards palladium. So hydride elimination can take place from here or from here. If it takes place from here, then in that case, we will get hydride elimination. Hydride will be eliminated from here. PD will leave this bond over here. So a double bond will be formed, RCH, CH2OH. This will be the product which will be formed. But if this hydrogen leaves as hydride, then in that case PD will leave the electron pair here. This bond will be broken. So we will get R CH2 CH CH OH. This enol will be formed, and this enol will tautomerize into the more stable ketonic form. And since carbon double bond oxygen is a harder bond, more stable as compared to the softer carbon-carbon bond, this will be the ketone, this will be the major product rather than this primary alcohol. So this was the second set of question on Heck reaction, indicating whether syn or anti, what type of an elimination is preferred. Since syn beta hydride elimination occurs and the insertion is also syn in Heck reaction, hence this product will be favored over this product in this case. And in this case, what will happen, the less substituted product will be the major product rather than the double bond being here and forming this more, because this would have been the more conjugated product, double bond, single bond, double bond, had this hydrogen been eliminated, because PD leaves the bond here or here depending on which hydrogen or hydride is eliminated. This hydride cannot be, hydrogen can't be eliminated as hydride because the elimination is also from the same side as PD. So here PD is dash, here this hydrogen is wedge. They are opposite, anti to each other, they are not syn. So this hydride won't leave. This hydrogen will leave as hydride, and so PD will leave this bond here, and we will get the less substituted product as the major product. So these were a few examples of the use of stereochemistry in our reaction mechanism, a knowledge of prochirality, chirality, prochiral surface, prochiral homomorphic ligands, and as to how there can be asymmetric induction if we have a prochiral phase. At the same time, another very important reaction and interesting reaction, the Negishi reaction, was discussed, which is similar to the Heck and the Still reaction, where we get cross-coupled products by using palladium as the catalyst. So thank you.